I'm Edgar Iglesias. I work for Xilinx, and I'll be talking today about how we use QEMU in our chip development and in our early software development. Okay, so I joined Xilinx early 2013, and at that point, Xilinx had just started a new chip project, and they had pretty aggressive targets for how to use QEMU, which was good. Basically, QEMU was supposed to be the first software platform available to write software on. And that included boot ROMs, bootloaders, any kind of firmware, hypervisors, and porting operating systems, and so on. Of course, there are a lot of issues with this when you're working on an upstream project. So schedules, if you really need to be the first platform available, maybe you can't wait until things get upstream. Or there's also secrecy involved, so you need to deal with kind of these cycles where you hack, and then later upstream, and so on. And that can be problematic, but yeah, it kind of works sometimes not. And there are a lot of benefits with using QEMU for chip development and for software development early when you're developing new chips. So compared to RTL simulations, QEMU is much faster, and it's also very easy to kind of deploy to many developers. There's no licensing issues in that sense, like you have to pay $1,000 per developer, things like that. I want to thank a few people at Xilinx before I start. So John and Peter Reiser that kind of believed in all these projects and been supporting us. Thanks for that. And the team that has been working from Xilinx. So Alistair is here, right there. Raise your hand, Alistair. Doing a lot of good stuff. Peter Crosthwaite, who unfortunately left Xilinx. So back when we started, it was Peter and myself. And Peter did a lot of cool stuff, and we did a lot of good work there. So we're going to miss Peter. And Sai, who unfortunately couldn't come here, but he's in our Hyderabad office, doing a lot of good stuff as well, so thanks for that. Okay, so this is one of the few public images of the ZynqMP SoC. I'm sticking to this so I don't leak information unintentionally. So if we look at it, we see that there's a real-time processing unit, the RPU, there's an APU. The RPU has Cortex R5s, and the APUs has the Cortex A53s. Then you can see there's a red box there with a security kind of block. I won't go too much into detail there, but you can say that there's a CPU there, a microblaze, and there's the platform management unit that has a microblaze as well. And there's a whole bunch of devices that need to be modeled. If you look at the yellow layer at the bottom, that's where the FPGA fabric is. So that's programmable logic, which you can or can't model in QEMU depending on what you want to do. But there are a lot of challenges in modeling this, especially if you look at QEMU 3 years ago. So I'm kind of going to walk through these challenges and how we solved them and how we worked with upstream to realize that. One of the things that comes with this aggressive targets for the platform is that when you have few resources, you basically have to scope out things, and some things were kind of impossible to achieve, so we kind of dropped those, and we targeted some of them depending on the criticality of the software we needed to get running. So there are trade-offs to do there. So one of the things we've been using for a while that's been quite successful, for us at least, is to not describe the machine in code. So instead we describe the machine in a device tree file, basically. And when we started using this, the goal was actually to use the same device tree as we passed to the kernel and pass that to QEMU to instantiate the virtual machine. There are issues with that. I mean, the fundamental issue is that the device tree you pass to the kernel is mainly used to describe the features of the hardware that the kernel can't probe. Whereas in QEMU, you need every detail so that you can instantiate exactly that piece or part or IP block or whatever. I mean, it's the idea is pretty simple. Just loop around and check the compatibility properties and instantiate the QM devices. For every property in a device tree node, we look up properties in QOM and can set those. And we can also deal with links and connect interrupts. And you can describe pretty complex stuff with this. Right. Okay. So this is let's say a very simplified approximation of the bus. So I showed the picture before, but that didn't really show the interconnect in any way. So I've simplified this, but you can see that there's the security and security configuration, which is a little bit of a special subsystem with local RAMs and local devices. We have the PMU, the R5s with local memory, a bunch of DMAs, and the A53s that bypass the first IOMMU. Then we actually have something that you could say is another IOMMU just for the discussion's sake. And then we have devices at the bottom. So when we started working on this, QEMU had no support for describing this kind of, let's say asymmetric views of the system from different CPUs. So that was one of the first things we did, to implement some kind of per master address space, so we can create different address views and for each master. This is mostly upstream. There's a few things missing. For example, the multiple address spaces per CPU. That's something that Peter is working on now or soon. Or we're also missing. I haven't checked lately, but I think we're missing like a unified way of configuring, telling a device, use this address space. What we want to achieve is basically to have a unified way to do that for CPUs and devices. We have a way in our tree, and we can actually instantiate all of that in the device trees. So you create the memory regions and attach those to devices and all of that. All right. Okay, so another pretty big challenge here back then was that neither the A53s or the R5s were modeled in QEMU. So the R5s were fairly easy because we already had the ARMv8, or a big chunk of it at least, modeled. The A53s were problematic though, because when we started there was nothing merged. So there were a few patches circulating. So Alexander Graf is not here now, but thank you very much for the initial port for EL0, I believe it was, Linux user. And then Peter Maydell and I guess some folks at Linaro got the EL1 working pretty quick, and all of that worked very well for us. So we could quite quickly get the kernel and user space going. The problem was, though, that we wanted to run more. We needed to run, port Xen and get KVM running on our platform, and get ARM trusted firmware running as well. And we have a whole bunch of code at Xilinx that we write for, validation, and all of those guys were writing code in EL3. So yeah, we need to do something about that. Basically, what we did is we scoped it down a little bit. We put the focus on AR64 and kind of bulldozed through that and prototyped EL2, including the virtual interrupts, the two-stage MMU, and the exception model, and the timers, and so on. Basically, just barely enough to get Xen and KVM running. Then a few funny things happened. Actually, at the Linaro Connect, we found out that no one was working on this. But then when we started posting patches, the whole thing exploded. And there was this guy, Fabian, from the Czech Republic. I don't know where he went after that because he disappeared. But he posted a lot of patches. And yeah, there was a lot of collaboration. And we've actually come quite far on this now. So thanks again to the Linaro people. Greg, who left Linaro, he did quite a lot of stuff there too. Fabian and Sergey from Samsung and more. So there's still a lot missing. The spec is humongous, like Mark said before. But yeah, we're getting there. I think we're actually quite close now with enough. EL3 is quite okay, and in EL2, maybe in 6 months. What do you say, Peter? Yeah, we're missing the two-stage MMU upstream and also the gig stuff. I think after that we'll probably be able to run hypervisors, but there's still a lot of incompleteness.
Xilinx QEMU is in public somewhere?
Yes, it is. Yeah. All right. Okay, so another thing that was problematic here is so I don't know if you're aware, but on the ARM buses, the AXI buses or AMBA buses, so when you send transactions, you don't only send the address, read write, and data. There's attributes that are kind of going along with the transactions, and so there's the non-secure bit used for TrustZone. There's also the master IDs that are, I think they're kind of a hack on top of the user bits or something. But anyway, they're commonly used to identify what master is accessing you. That's important for the IOMMUs. Right, so actually when we started working on this, we kind of looked at the memory attributes and it looks kind of messy. And we already had the address spaces going, so because we did a first shot at doing kind of the security extensions for the gig, just using address spaces. Basically, having the CPU have two address spaces, and for secure accesses, you would actually access a different memory region in the gig. And that worked okay, but it fell apart very badly when you start doing the IOMMUs. Because you need to have a port for every master, and if it's secure or non-secure, and then once you get out of the first IOMMU, it kind of explodes. So the code for IOMMU is, the actual code is a small part compared to all this decoding of address spaces and translation. So, right. So we did actually an implementation of the memory attributes that we are using at Xilinx today. Now, when I was talking to Peter at Linaro Connect, he was working on an alternative, and eventually his version got merged. But we're pretty happy with that, so that's looking good for our needs. Maybe some slight difference that we have that, I don't know, maybe we can add that later in upstream, is that we use our memory attributes are actually QOM objects. And that's useful for us because that makes it very easy to instantiate them in the device tree and then just attach them to whatever master that needs to use them. Okay, yeah, like I mentioned, the IOMMUs were non-trivial there without the attributes. It was a bit easier with the attributes, but it's still quite complex to get this right, and there were a few things, bits and pieces missing for doing IOMMUs behind CPUs. That's still something we need to upstream. But it was immensely helpful to get stuff running. We actually had a bug in Xen and in our RTL that would have been so hard to find without kind of being able to debug the hardware model. Okay, this is going quite fast. Actually. Does anyone have any questions so far? Or no? Yeah?
What bug you had found in the SMMU driver in Xen?
I don't know. Yeah, you're aware. So in Xen, and I think this differs from KVM. In Xen, when you use the SMMU on ARM, you actually share the second stage page table with the CPU. And the critical thing there is that they have to match. The configuration of those page tables have to match. And in Xen, they were kind of ignoring the topology of the SMMU when they created those page tables and assuming that that the SMMU would kind of be able to use that configuration kind of by default, and that wasn't the case. So it was quite trivial. The fix was trivial, basically to set up the SMMU the same way as the second stage MMU.
So I can understand. So the MMU, the page table for the CPU.
Yes, second stage.
The second stage is not usable with SMMU?
Yes, it is, but you have to configure the SMMU in the exact same way you configure the second stage MMU in the CPU. So you know how for example, the input size of the address matters how you walk. It affects how you walk the page tables. So if you don't get all those details right, you're gonna walk the page table differently, basically. Okay. That's partly. We fixed some of them to get our stuff working, but there's still some missing that we need to fix. No more other, yeah. No, we scoped it down pretty much. So we did the AR64, and I think there's quite a lot missing. A lot of the traps were missing. I mean, our goal was basically to get the exception model going, so you could do SMCs back and forth, so we could program the ARM trusted firmware and add our additions in there. So stuff beyond that we really didn't care of. But there's a lot that has been done since then by Linaro and this guy Fabian. So yeah, it's looking pretty good. There's still stuff missing, but yeah.
The second question is, did you have any trouble modeling both M series and R series CPUs in the same QEMU instance? Because they're asymmetric.
Sorry, do you mean the modeling we didn't have an M series? Or you mean when we actually...
sorry, A series. Both the A series and the R series CPUs.
Right, I'm coming to that now.
Oh, okay.
All right. Okay, so... yeah, another thing you may have noticed here is that we had, so there's 2 microblaze, there's 2 R5s, and there's 4 A53s. And when you when you build and run QEMU today, you build it for a specific architecture. You can't run different kinds. So actually, when we started looking at that, the AR64 build, the ARMv8 build, let's say, it includes all the 32-bit machines as well. So we did a quick test and just instantiated the R5s we had with the A53s on the same machine, and it actually just worked. So that wasn't really a problem. If I remember correctly, there was nothing we did. Now, the problem comes when you want to have the microbases in there. So we were looking a little bit at the tree then, and I was a little bit unsure what the state was. I know that Andreas, I think I saw you. Oh, there you are. Andreas did a lot of good work on trying to, clean up the code to eventually walk towards a clean multi-arch implementation. So, but back then when I looked at it, I didn't think we would make it basically with the time constraints we had. So we went and did another approach. Having said that, now very recently, so Peter Crossway posted some patches to kind of achieve the multi-arch within the tree in a single QEMU instance. And Xilinx has been, so we partnered up with Green SoC. Fred is there. Thanks for all the good work, Fred. To do the multi-threaded TCG, because once we have both of them together, it's going to be really good. One of them only is not that good for us, because I mean, if you get the multi-arch but don't have the multi-threading, and you're doing AMP, the CPU is running the small kernels that don't do interrupts. Maybe they're going to consume all the time. And if you have multi-threaded but now multi-arch, it doesn't help us very much. So we need both, actually. At Xilinx. The community probably is happy with one of them at a time. Okay, yeah, so thanks to Green SoC there, and thanks to Andreas. Okay, so what did we do? We did, so I've heard it mentioned here a few times already in this conference. We did a kind of a QEMU to QEMU proxy, and it uses shared memory and Unix sockets to communicate. Actually, the first version we did, we tried to use QTest as a proof of concept, because I figured, using QTest, it won't be that controversial. Slowly adding a few patches to QTest, and suddenly we'll sneak in a QEMU to QEMU protocol into QEMU. But nah, we gave up on that quite fast. And it's so inefficient with all the text thing. And so we did a kind of a binary version of it, and then we did the shared memory. Right, so you can connect, QEMU can be a bus master on the QEMU side, accessing slaves on another process. Actually, the other process doesn't have to run QEMU. It can be anything, as long as you implement the protocol. Can also do, so QEMU has slave ports. You can do GPIOs, and we use the DMA stream objects or classes in QEMU to abstract DMA transactions, you could say. And there's a bit of stuff there for synchronization and atomic ops. So for example, if the microbase does an exclusive access on something, so you can actually get that working between the microbases and the ARM. Another thing that was cool is that because they're running in separate processes, they actually run in really parallel. It can get very messy if you start thinking about where you're going to do the cuts, where are you going to connect the different machines at. But we did it just the simplest way, because it got too messy if you try to make the cut deep into the device land, or try to do it realistic with the real hardware or anything like that. The easiest way is just to cut it, basically have a CPU in the foreign instances and have all the devices in one QEMU. And that was kind of the approach. There were a few things that sneaked out, but basically that's the approach. We have a big instance running all the ARM stuff, and then we have 2 remote instances running the microblases. And that worked out very well. That's what we're using today to bring up the entire system. Any questions on that?
But there's not so much traffic between the microplaces and ARMs,
right?
It's more like configuration.
Exactly. There's a bit of there's a few interrupts going between the PMU, because the PMU is actually responsible for power management as well. So if the ARM wants to power up something or use something, it needs to signal. So there's a bit of, let's say, remote processor communication, but it's not much. And even if there was much, it's still quick, because you're using shared. You're not actually sending memory transactions on the Unix sockets. You're just accessing the memory. Okay. More questions? Right, so I already talked a little bit about this. The shared memory was quite easy to do. Actually, we already have the mem path, so we added a shared version of that. And the mem path actually creates files on your file system that it maps in. And those files are named based on the device, the name of the RAM in QEMU. So just making the RAM name being the same across all instances pretty much solved it. And it's nice that you can also use any Unix tool to inspect the memory. So you don't have to use GDB to look at the memory, or if you want to load something, you can use any tool to kind of put stuff into the memory, which is interesting. Right, I already talked a little bit about this. We didn't implement, this is something that's missing. We were thinking about it, but we actually never needed it yet. And it's the case where one of the instances actually touches memory that is in QEMU cache of the other instance that's already been translated, so it's in the TB cache. So if you touch that code, the other side is cache won't flush. So we just haven't had that use case yet, but it is solvable somehow, I guess. Okay, questions so far? So another big chunk here that's tricky is the, let me just see where I'm at. Yeah, it's the yellow part. What are we going to do about the PL? People that want to run some kind of little RTL down there and do something with that. All right. Okay, so you're probably familiar. This has been on the list many times, but System-C. So it's a C++ class library, let's say, for simulating hardware. It's kind of like QEMU's framework, but a little bit more low level, and it actually has different levels of abstractions you can choose from. You can choose a very low level, modeling at kind of gate level, or you can go up in the abstraction level. And on top of System-C, or kind of next to System-C, there's a standard called TLM that provides a way to interconnect or interoperate models at a very high level. And this is actually quite similar to QEMU's say memory region and the whole device model. It's different, but it's kind of the same thing. So there's open source simulators for System-C and TLM, the OSCE ones, and they work well. And System-C TLM is increasingly popular by chip design teams. And it plays a very important role when you want to glue models together that may be written in different languages and different abstraction levels. So you can have a model for a timer written in Verilog, and if you create a System-C glue around that, you can connect it easily to a model written in VHDL or in C, and so on. So what we did was basically wrap the remote port with System-C and TLM. So what you see from the System-C side is basically a TLM compatible device, and you don't actually need to know that there's a QEMU on the other side. And there's a tool called VeryLater. I don't know if you heard of that, but it's an open source tool that translates Verilog to System-C, and it all just pretty much plays together. So that's pretty cool. And we actually use this in some of the debugging to run. We ran the entire system except one device in RTL, and if you do that, it actually models very fast. It's significantly slower than a pure QEMU, but maybe times 3, or it's not like RTL where you wait days for something. So full RTL where you wait days. So that was good. And the nice thing is that it's a full open source flow because the whole System-C thing is open source, and the VeryLater is open source. And right. Okay. So some of the details there. When we run QEMU, we run it with iCount, specifically when we're using the System-C things, and that's to control the timing. Because we don't want QEMU kind of running away too far off from the System-C times. We want to keep them kind of in sync. And in System-C, there's a concept of a quantum that allows you to specify how far ahead you let different models go. And if you make the quantum small, you get kind of quite accurate, lockstep kind of simulations. But if you make the quantum high, things can be far apart from each other, but you get better performance. So that's like a knob you have to control that. And there's other ways you can do to kind of time warping to increase the speed. Okay, and remote port is actually, it's not, we never attempted to upstream it, but it's out in a public tree. It's a bit old, though we haven't rebased. It's probably 2 years old or something like that, the tree, but yeah, we'll see what happens with that. Yeah, I was talking about VeryLater. That's a very nice tool. Right, and you can use a full open source based flow and actually do hardware design, which is quite cool, I feel. Okay, some other stuff we did. Some tools to ease debugging. We added a binary tracer that basically dumps the execution flow and some other info as well. All the interrupts that are signaled, memory accesses, in a kind of efficient way, binary. And then we have an external tool that post-processes that. And it can post-process the traces or connect kind of through a socket to post-process live. And the reason you want to post-process live is if you're doing code coverage and running long runs, because the traces get quite big quickly. Right, so this is the external tool, the QEMU trace. And you can pass it L files with DebugInfo, and you'll decode those and kind of keep track of which source lines that have executed how many times. And based on that, we generate an LCOV info file. And from there, you can go and generate the beautiful web pages. And yeah. Some more debugging stuff here. An interesting thing we use is that if any of the models issues a log guest error log, we break the GDB sessions if there's any attached. That can be useful because if you're debugging the code, the debugger will actually break on the exact line where you commit let's say, a memory MMIO access that is no good. Instead of maybe breaking much later when you start a DMA transaction or where you're doing something else and the hardware starts operating on that bit that you misconfigured. So that can be useful in some cases. There's a few ARMv8 things we did to kind of easily switch between ELs, different EL views from the GDB client. Something we had problems with, which we haven't solved, is that it's quite hard to do the run state control with the current QEMU, because if you start one of the CPUs, I think we enter this loop and kind of start running all CPUs, and it goes a little bit crazy. I don't know if you know about that, Jan. Yeah, there's some issues there. I don't know. Should probably look at that. Okay, yeah, this was interesting too. We did a little bit of work, and hopefully we'll do more of this with Green Socks and Fred. With the Q-testing. So back then, Q-test, I think Anthony added Q-test a long time ago, no? Well, I don't know. Anyway, it was added, so maybe not everyone is familiar with it. Q-test is a protocol in QEMU to which you can attach another application to and kind of do a few things in QEMU, kind of memory accesses. You can check the value of an interrupt. And Andreas, anything else you can do there? Do you remember? Right. Right. You can kind of single step, no? Step 1 I counter. Right. Right. So okay, the initial intention when it was added anyway was to be able to test device models from some kind of test suite. Like unit tests for a device model. And there's many of those now, and I know Andreas has added quite a few, no? So, right. So what we wanted to do was actually to use this to test not only models, or not really models in our case, but test the software running, the embedded software. So we added support for running QTest together with TCG CPUs, and that's upstream now. That was just a one-liner. And then we wrote a Python class that exposes the QEMU machine over. So you write a Python script on the side, you connect to QEMU, and then you get an instance that, let's say we call it QEMU here, and then you can do 32-bit bus transactions. It exposes the memory as an array, basically. You just so this line here is doing a 32-bit write to address 1000 in hex and writing the A0. The next line is reading from the same address, 2 bytes, and we added support for setting signals as well, so artificially raising interrupts. And we started writing tests like this, but eventually it kind of bit rotten, unfortunately. But this is something we really want to pick up again, because I think there's a lot of value in that.
Where does the APU name come from as a field there?
Oh, the application programming unit. That was the blue box in the.
I mean, I understand the abbreviation. I'm just wondering, are you, parsing the QOM tree to actually get those names, or how do you get those fields there?
No, I think that was that was the script just naming things like that. So no parsing. Right, but you could do that. That's a good point. You could, I guess, parse it and kind of. That's a good point. Okay, but I think there's a lot of potential in this kind of stuff for validating, boot ROMs and sensitive software where it may be hard to trig. Yeah, so an example could be, let's say you have software that reacts on a heat sensor, or it reacts on humidity or something like that, and it can be quite hard, to trig all the use cases, all the corner cases, in the software. So by having mechanisms where you can trig stuff from the outside in a controlled way, together with, so this is another thing we want to do, connect this to the code coverage, so you can have a closed loop where you have a Python script that can, trig events basically randomly and measure code coverage, and run that for a couple of days and boom. Yeah, I think that could be very useful. So if people want projects to hack on, QTest. Okay, another thing here, the RTL Designers. I guess this happens everywhere, but in their world, it's very common that you go from some kind of specification of registers, and you generate the RTL, you generate documentation for the device, all from one source. So this was something we wanted to use, because when we started, actually, we were writing all of this stuff manually. That bit is read-write, that bit is read-only, that bit's reserved, that bit is clear on write, and all of that. So we wrote a little bit of a backend to our tool there to auto-generate like a skeleton for a QEMU model with all the register accesses, all the policies basically pre-programmed. It's not, it doesn't give you a useful model to start with, but all you need to do is basically fill in the logic, the actual logic of your device. So that's useful for some for example, the ARM SMMU, we auto-generated most of the stuff, and that beast has thousands and thousands of registers. Let's see. Right. So actually, we added support for identifying interrupt logic and interrupt controllers. So you can generate an interrupt controller. That's the only device it can generate fully useful from the spec. Yeah, one more thing to add here is that there's the tool here actually uses the register API that's been on list a few times. That's something Peter Crostwaite was working on, which is quite a useful way of having a data-driven way to describe registers and the fields and how the access patterns and so on. All right, that was all I had. Any more questions?
For the stuff you've published, if it's not upstream, where can I find it?
Yeah, can I get back to you, Alistair, actually? Because I've been off for a month, so I've been a little bit lost on what's been published lately, but Alistair has it.
Thanks.
So Edgar, you've been a bit modest in the first slide, so I wanted to really repeat this so that everyone really gets this. So the work that his team has done was actually making a press announcement about their new chip model availability, and they had patches for U-boot, the Linux kernel, and QEMU out on like the same day or pretty much about really that date. So really, I would like people to give a great applause to Xilinx for embracing QEMU as a development platform.
Thanks, Andreas.
Now, having said that, could you give us a bit more background of what QEMU means to Xilinx? Because right now it seems that you're the only chip vendor that I know that has embraced QEMU to the same level. For instance, your competitor Altera, if I may name them, they stick with the proprietary Synopsys solution. ARM has their proprietary solution that some other vendors are using. What is the real value of using QEMU to you at Xilinx?
Right. Yeah, I guess there are kind of multiple fronts on that. But this being, I guess, the first project at Xilinx where QEMU has been this heavily used, and I feel it's been a quite big success. So it's been an eye-opener for many at Axis or Xilinx how much you can actually do with it and how much time you can win in the early days. I think the level of importance is very high. We have Vina here also from the Xilinx team, and since she can acknowledge that. Actually, this wasn't maybe planned from the start. The start of the project was very focused on getting a platform for internal use. But now we're actually planning to, work to get this out to customers so they can also develop and using the same stuff. Now what we have, we haven't been that bad, but we haven't been very good with the upstreaming during the process. And I hope that's going to improve once, the short-term model. We actually have other modeling solutions now, and we quite soon are going to get real hardware. I guess it's scheduled for early next year now, availability. So once that happens, I hope we're going to get more time to, get all of this upstream. Because what I envision is that next time around for the next chip, we're going to be even more aggressive. And we want all of this stuff to be available, if possible. Whatever the community feels is good. And so next time we don't have to reinvent as much, and we can focus on the new stuff. Yeah.
But to drill a little further, is this something that is being driven by your customers asking for it? Or is this because, QEMU offers better feature set or more freedom to implement things than other solutions? Or, what is the main motivator to go with this route?
Okay, yeah, so I don't think our customers specifically ask for QEMU. They don't really know maybe at that level, but Some of them do. Yawn back there. But they do ask for solutions that can be achieved with QEMU. And I mean, Xilinx has been down the path of trying other solutions. And I'm not sure if the other solutions are going to stop. I don't think so. We're going to have multiple ways of doing it. But the QEMU ways is very attractive also because of the licensing issue. If you do, I don't know, I don't want to talk bad. I mean, ARM does a lot of good stuff. But for example, the foundation models or the fast models, there's a licensing cost involved with that. So if you want to distribute that to 300 developers, it becomes very expensive. Whereas a QEMU-based solution with System-C could potentially, depending on what the IP, of course, but could potentially be very cheap to distribute for a customer. And as far as I know, our plans is to publish QEMU pretty much free. Yeah, because the goal is ultimately to sell more chips and to enable more people to do stuff with our chips. Yeah.
Okay, thanks.
Thanks.
Do you have any examples there of the FDT files used to configure the...
Yes, I do. I'm not sure. I'll scare people away if I show it here, but okay, I can give it a try. Actually, I'm not sure I can. I can show you a small one. There's still a little bit of secrecy in there, and I'm not sure. I don't want to show too much here, but this is pretty nasty. But okay, so for example here, there's of course there's a macro here, but if you ignore that, this device here will actually instantiate a memory attribute object, a QOM object, and it will set this secure property of that object to be secure, and you can select the master ID, and then we use the macro to instantiate a few of them. I can maybe show you the... Yeah, I'm not sure what I can show you here without leaking. Okay. Should be fine? Let's do the... maybe the PMU QTS. Right, so here's one with... so here's basically the PMU block, instantiating CPUs. And as you can see here, the list of attributes is huge because we need all of them to instantiate the exact model. Let me make this big here. Is this readable? No? Okay. So you see, that's just configuration of the CPU. Actually, Alistair has been working on converting this. Basically, we have all of these options in Microblaze, in the Microblaze model of QEMU, but we didn't have them as properties. We basically had registers that the board model edit. And Alistair is converting that now. Right, so now they're being converted to proper QM properties.
So when Anthony came up with the QEM concept, one of his goals had been to drive the machine definition through config files. So I wonder, do you rely on having the DTB to device instantiation code inside QEMU, or would it be possible to have that as an external tool?
Right, so I remember that was one of the comments when we tried to upstream. And we have it inside today, but there is no reason why it really needs to be there. It could very well be a I mean, if there was a QMP way of, for example, creating the connections from a remote, let's say a Python script that parses device tree or another format and can kind of from remote gradually create the machine, that would work too. Is that what you meant, or?
Yeah, kind of. So I'm guessing what's problematic there is probably still the ZysBus devices with the memory mappings, with the memory regions, or what is currently stopping us from doing that from Python scripts?
Just generally create common text. I think there's probably the SysBus. I think there's nothing that's a showstopper.
Well, the QEMU IQ maybe.
A lot of the SysBus stuff is just the C.
So maybe summarize it as known problems that people have somewhere down their to-do list, right?
Right, but I don't think we have awfully many patches to enable this in our tree. Most of that has been upstream. Yeah, I don't think so. I may be lying a little bit, but I don't think so. I mean, there's all of the FDT parsing, but beyond that, I don't know. I don't think there's so much. Right. Okay, so this is what it looks like, and when we create the RAMs, here's a memory region. You can see the bus for the PMU. Right, and if we have the multi-arch setup, we instantiate the remote port devices here. So here we got a memory master listening at specific addresses. So this is basically a memory region in QEMU, and when you write an MMIO region, when you write to that, it's going to convert memory reads and writes into remote port transactions. Okay. I'm out of time here. Thank you, guys.